use modeling, numerical modeling, analytical modeling techniques to describe that behavior. And here again, the specific focus of my research has been on acoustics and the field of phononics. I will talk a bit more about what phononics and metamaterials are later in this lecture. So the agenda for this talk is outlined here as follows. I will start with a short introduction of my career path and talk a bit about past research projects, specifically the acoustic microsensors. We're not fully familiar with CAM. And finally, I will introduce the research projects of our newest PhD students, what they are doing and what they are going to do in the next few years. In the end, I would like to conclude with acknowledgement and thanks to all the collaborators and colleagues that I have worked with in the past. So let's start with where I come from and how I managed to obtain this position here at DTU. So originally I grew up in a town called Magdeburg, which is relatively in the center of Germany, between Hanover and Berlin. And at the Otto von Guericke University in Magdeburg, I studied microsystems technology, so MEMS devices, how to build them, how they work, and what to do with them. During that time, I also had multiple international stays, especially at the University of Neuchâtel in Switzerland, where the institute is now part of EPFL, where I worked on microfluidic devices, microfluidic pumps. For my PhD, I moved to the city of Linz in Austria, where I studied acoustic microsystems at the group of Professor Bernhard Jacobi at the Institute for Microelectronics and Microsensors. After finishing my PhD, I moved on to work together with the Austrian Center of Competence in Mechatronics, ACCM, as it was called at the time, to work on multiple projects with industry partners with different companies. I'll give a short glimpse on what kind of projects I worked on there. In 2014, I moved to the city of Bremen in northern Germany, where I joined the Institute for Microsensors, Actuators and Systems and the group of Professor Wellekoop. And there I became responsible for the technology field of additive manufacturing and how to exploit that new technology for microsystems, microsensors and devices. I also employed that technology then for phononic crystals and metamaterials, which again I will talk about in a bit. And finally, in 2020, so beginning of this year, I became the professor and head of the Center for Acoustic Mechanical Microsystems here at DTU. And I'm looking very much forward to continue and expand my area of research here. So I mentioned microsensors and acoustic microsensors already quite a bit. It's also in the title. So let me just quickly give an introduction of what an acoustic sensor, or what I mean when I talk about acoustic sensors. Acoustic sensors can operate on all frequency ranges, but when we are talking about a sensor, so a miniature device that interacts with an environment, with a material, with a medium, we are typically talking about two kinds: ultrasonic sensors, which send an acoustic wave, an acoustic pulse, into the medium, and then the received signal or the reflected signal is analyzed, and we can determine properties of the medium, properties of a liquid, or for example the flow rate of the liquid. You all are encountering ultrasonic sensors all the time because they are used, for example, in cars for the parking assistance. They are used in sliding doors, automatic sliding doors, so that they open automatically, where they propagate an ultrasonic pulse through air. And on the other hand, we also have what is called resonance sensors. Here, we do not necessarily transmit a wave into a medium, but rather we create a standing wave inside a resonator, inside a finite structure. And then we bring this resonating, this vibrating structure into contact with the medium. And by putting it into contact with the medium, we will generate an acoustic load. And this will change the resonance behavior of the device. And then again, we can deduce what kind of properties the medium has. In my research, I've mostly focused on resonance sensors and using the electromagnetic transduction principle to excite them. This electromagnetic principle is based on currents superposed by a magnetic field, which result in Lorentz forces. This is kind of sketched in this graph here. And these Lorentz forces put the element into vibration, and depending on how we arrange the direction of the current, the direction of the magnetic field, we will get different directions of the Lorentz forces, and it can excite different modes of vibration in such an element. Just as an example, if we excite this shear motion, so where the plate only, in this case, rotates, so the surface only moves in plane, we will generate, and then we put it into contact with the liquid, we will generate what is called an evanescent wave, so an exponentially decaying wave, not propagating, but just penetrating the liquid. And this evanescent part of the wave is very much dependent on the material properties of the medium, for example, density and viscosity. And therefore, by measuring the behavior of the resonator, by looking at this standing wave and how it changes, we can see that it results in a frequency shift and in a change of the resonance depending on what kind of liquid we have, what kind of density, what kind of viscosity this liquid has, and therefore we have a sensor to measure density and viscosity. Analytically, we can look at it as a viscous load, as a liquid load affecting the acoustic resonator. In contrast, if we use the Lorentz forces to excite an out-of-plane motion, so a motion where the resonator, the same resonator element in this case, exhibits a flexural motion, we will generate or we will radiate waves into the surrounding medium. And these waves, like an ultrasonic sensor, will give us an information about the properties of the medium. If there's, for example, a surface level at a certain distance, we can generate an interference pattern, as indicated also in this graph. And this interference pattern will tell us something about the liquid level, so the height of the liquid in our measurement cell. So that is a way to very precisely define the height of a liquid in a tank, in a container, or like other samples. This can be modeled also analytically, or at least approximated by a transmission line. We are here at electrical engineering, and a transmission line, especially a lossy transmission line, very much shows a similar interference pattern. So constructive and destructive interference. And this again acts as the acoustic load to our mechanical or acoustic resonator. One of the projects that we did with our industry partners, in this case the company called Anton Paar, who built laboratory instruments to measure density, viscosity, speed of sound, and radiometric properties. These are bulky, expensive laboratory machines. And in this project, we explored how to make a very simple, inexpensive measurement cell to again also measure those properties, so to measure density and viscosity specifically. Here, we also used the electromagnetic excitation principle, and we have a metal plate, a metal suspended plate by 4 anchors, and when we run a current through those anchors and superpose it with a magnetic field from some permanent magnets, we will again generate Lorentz forces and put this suspended plate into motion. And the motion you can see here at the bottom. So we have an in-plane motion again of this suspended plate, and therefore it's very sensitive to the density and viscosity of the liquid. And you can see the result in those graphs where we have a linear relationship between the frequency and the damping for different kinds of liquids over a wide range of densities and viscosities. And the whole setup is very inexpensive. It's just a couple of layers of printed circuit boards, 2 permanent magnets, and this structured metal resonator. So there's no expensive electronics or moving parts other than the vibrating element involved. Besides that research on acoustic sensors, I've also worked in projects on MEMS materials, and I'll try to make a link with the acoustic sensors in a minute. The idea of this project, together with a company who works as a supplier for the automotive industry, was to find a new material that exhibits superior thermal properties, thermal characteristics, compared to the standard samples or standard substrates that were used for thermal micro devices. Thermal micro devices are, for example, heaters that react very quickly and that are used in engine control, in exhaust analyzing, or catalytic sensors and similar events, similar devices that are used in a combustion engine. Typically, these devices are built on a fragile glass or silicon nitride substrate. And here we explored if there's any other material that has a better mechanical stability, is less fragile, but has a similar thermal insulation behavior. And there we found what is called porous silicon. So taking a sample of silicon, single crystalline silicon, and making essentially holes in it. But not just any holes, but very tiny holes. So we are looking at holes on the order of a few 10 nanometers, what is called the so-called mesoporous regime. Why do we need those holes on the order of 10 nanometers? Because that's the dimension that is quite similar to the mean free path of thermal phonons. So we structure the material, these are the samples that we produced, on the order of the wavelength of the physical property that we want to affect. And as you can see in those figures, we reduced the very high thermal conductivity of pure silicon to more or less the same order of conductivity as glass and silicon nitride, simply by this microstructuring. And you can see also that the porosity, so the amount of holes versus remaining solid volume, is not very high. But even though it's only about 50% porosity, we can reduce the thermal conductivity by orders of magnitude, with more than you would expect if you would think about it just as a mixture of materials. And we'll come back this is the takeaway from this project. Microstructuring a material allows you to change the physical properties way out of or way away from the natural occurring physical properties. Just to show you that this device also then works, so this is the microheater placed on the porous silicon substrate, and in these thermal images, these thermal photographs, you can see that the behavior is essentially the same between glass and porous silicon substrate, where the porous silicon substrate actually outperforms the behavior of glass. Okay, so the idea of microstructuring a material to affect its physical properties in ways that is not normally possible will find its way to the field of metamaterials and phononic crystals. But before I go there, I want to talk about additive manufacturing, 3D printing, and how that can be used to actually create those microstructures. This is a slide with many pictures, I know, but I just want to highlight all the different kinds of things that you can do with 3D printing. And that's by far not all, that's just the things that I've been involved in, some of the things that I've been involved in where we use 3D printing to make research easier, or even just to enable research on a specific topic by having the capability of building a custom geometry. Just to pick out one example, this is a macroscopic example where a student of mine 3D printed a loudspeaker. So here only the permanent magnet and the voice coil of this device were not 3D printed, everything else was 3D printed, and despite everything being made out of a kind of plastic, it still worked and sounded relatively good. One big advantage of 3D printing is the connection of microchips to the macroscopic world. I mentioned that in the beginning. You can take a microchip, for example a microfluidic chip, where you want to inject some liquid, analyze the liquid, and then eject it from the microchip, and combine it with a 3D printed holder that allows you to customize the way it connects to the macro world. Previously, before we had this capability, you had to use expensive throwaway connectors that are typically glued to the microchip, and you can imagine that that is not a very reproducible and useful way to handle these devices. But with 3D printing, we can connect the fluidic part, an optical part, optical axis, and also the electrical part very easily to any kind of microchip design that we have. And on the micro scale, these are the bottom pictures, we can print even very small and fine details down to a micrometer in size and even below using a technique called two-photon polymerization. And the examples here are just a micromixer and a filter in a microchannel and a micromixer. And this interesting example that is an ongoing research project still at the University of Bremen, where we build these cage-like structures which look a bit like a football net, but instead of catching a football, we are catching a single biological cell. And in this way, we can control where this single biological cell is located on our chip, and therefore can very exactly analyze, for example, using an optical microscope or optical interrogation techniques, or also capacitive or impedance measurements, as is indicated by this light part, which is an electrode. So additive manufacturing allows us to do many things, and many different structures can be realized. This brings us to the field of metamaterials and phononic crystals. But before I go into detail of how we... And the way to achieve that is, as before, by the microstructure, by achieving a certain composite behavior, creating a composite material. And this composite material can be periodic, so regularly arranged, semi-periodic. It can also be not periodic at all. But when we talk about phononic crystals, we are talking about a periodic arrangement of this microstructure. An example is shown here. This is an art sculpture which is in the city of Madrid, and it's actually the first demonstration of a phononic crystal in the real world. And people have then taken that also to very small regimes. You can see this is a MEMS device, so a microstructured device which is actually used to affect not sound or vibrations, but thermal phonons again. So the idea, by having this regular structure, here this regular arrangement of rods in air, or here this regular arrangement of holes in a solid matrix, in a silicon matrix, we can create a behavior not found in either the matrix material or the scattering material. And the way to describe this behavior can be done with a so-called acoustic or elastic band structure. If you have ever heard something about semiconductors, you will be familiar with an electronic band structure, with a semiconductor band structure, where there's a forbidden band which electrons cannot inhabit. And likewise, here we are talking about a band structure that can exhibit these forbidden bands, these frequency regions where acoustic waves cannot propagate through the device, through the structure. Besides this band gap, which in the original phononic crystals is created by what is called Bragg scattering, we also have what is called local resonator effects. So small resonators, microstructured resonators that absorb energy at specific frequencies, which then again lead to a band gap, or a region where the wave cannot propagate through the material. And that is how we come to the field of metamaterials, where instead of having this regular arrangement on the order of the wavelength, so the lattice constant, the dimension of this arrangement is on the order of the wavelength that is affected, For metamaterials, some examples, some 3D printed examples here below, we can have a much larger wavelength affected by a small device, so we can affect much lower frequencies. My idea, my approach at that time was then to combine the technology with the physical behavior, with the physics. So to use additive manufacturing to realize complex phononic crystals, complex metamaterials. As you've seen before, the classic phononic crystal is a lattice of a regular scatterer in a matrix. Could be a hole in a solid substrate. So the first logical extension of that would be to have a three-dimensional matrix with 3 holes. And indeed, this would be a 3D printed sample using this design. And we can see in the graph below that going from the 2-dimensional arrangement, the light blue one, to the 3-dimensional arrangement of holes, we can drastically change and increase the width of the phononic bandgap, the frequency region where no wave transmission is possible. But why stop there? We can, as you can see, there are multiple other designs that can be explored, including these, let's call them ball and beam structures. If we look into those ball and beam structures, we will notice that they exhibit more than just the so-called backscattering. They exhibit local resonance. And why do they exhibit resonance? Because essentially they are a combination of masses and springs, a regular arrangement of masses and springs in a 3-dimensional lattice. And indeed, you can calculate or you can set up this 3-dimensional arrangement of masses and springs, look at the interaction between a single mass and its nearest neighbor or its next nearest neighbor. I won't go into the formulas, don't worry. And calculate which kind of vibrations, which kind of acoustic waves can propagate through that structure. And you will find that there's an upper limit of how much or how the waves can propagate it, which is synonymous with the lower limit of the first band gap. And this lower limit is very low, is orders of magnitude below the backscattering frequencies. And by tuning the geometric properties and optimizing the whole mass and spring arrangement, we can optimize and maximize this band gap, the width of the band gap, and also the position of the lower frequency. And this is exactly what we have done. These are some 3D printed samples, photography samples, so they were not used for measurement, just for illustrating the 3-dimensional structure. So you see it's a mass or ball and beam structure with big masses and thin beams. And this arrangement indeed shows a very wide band gap, which was at the time the largest and widest band gap reported in literature until very recently. Beyond that, we can also explore more complex lattices. This is a collaboration with some colleagues from Greece, where, as you can see, we are not limited to this cubic arrangement or simple cubic arrangement, but have a much more complex structure that we want to explore. And for anyone who took a course or heard anything about crystallography, you will know that there are many, many more crystallographic arrangements available in nature or in technology. So we are just scratching the surface here. We can expect that any kind of lattice arrangement can exhibit unique band structures that we can exploit for certain effects. But we don't have to stop with 3D structures, with normal Cartesian arrangements. But we can also look, for example, at these tubular structures, or we have actually looked at these tubular structures, where instead of having 3 translational symmetries, we now have 1 translational symmetry along the length of the tube and 1 cylindrical symmetry along the circumference of the tube. Again, 3D printing allows us to realize that behavior, whereas in traditional machining or traditional fabrication, realizing this tube structure would be quite difficult. And again, in nature or in industry are transported through pipes and tubes, like your blood vessels in your body or the pipes and tubes in a big industrial plant. While flowing through a pipeline, you don't want to disturb the inside of the tube. But as you see, we only change the outside of the tube. There's no disturbance of the inside. That's still the inner tube. We only have this regular arrangement of rings, of resonators, along the length of the tube. And by doing that and exciting it with an acoustic wave, with a vibration, we can generate what are called cavity resonances inside the liquid. And I mentioned that before. If we have a resonance, it will be dependent on the liquid properties. So we can measure the liquid, the fluid flow, and other behavior. Center for Acoustic Mechanical Microsystems, for those not fully familiar with what we do and who we are. One of the research projects that I would like to discuss in a bit more detail is now being continued by Jaugen and as a PhD project. And the idea here is to build what I call a phononic fluidic cavity sensor. So in contrast to the initial acoustic sensor, where we designed the resonator and put it into contact with the liquid, we now create a liquid volume, which is the resonator. So a cavity which acts as a resonator, where we have a standing wave propagating through the volume and giving us information about the volumetric properties, about the bulk properties of the liquid. And with that information, we can then say something about concentrations, about reactions happening in the liquid, and other environmental changes. So again, in contrast to before, we are not focusing on the transducers, but really on the design of the liquid, of the fluid volume. Combining this with 3D printing allows us to create a sensor element without worrying about the more expensive transducers, and therefore creating a disposable device that can be reused or thrown away, and another one is taking its place. The concept of this cavity resonator and this cavity sensor is as follows. We start with the phononic crystal, and this defect resonance is directly dependent on the properties of the liquid inside the cavity. So changing the liquid changes the resonance frequency. And therefore we have direct access to the bulk properties, especially to the speed of sound, density and compressibility, and also viscosity of the liquid that we want to analyze. The type of phononic crystals that we use outside this fluidic cavity can be any of those structures that we have studied before, or any other kind of structure, but some will work better, some will work less well to create the desired resonance peak, but all will see a frequency shift of the resonance depending on the liquid. And for an optimized design or an optimized initial design, we can see that we can use this as a concentration sensor to measure the concentration, for example, of salt and sugar in a water solution over a very wide concentration range. This basically covers the complete solubility range of salt and sugar, which is something that other types of sensors often cannot do. They are good for very low concentrations or good for very high concentrations, but covering the complete range is relatively unusual. And we also have a very linear relationship between the concentration and our resonance frequency. And the achieved sensitivity and resolution of this device is quite competitive compared to other results of acoustic devices found in the literature. So again, this project is continued by Jaugen in his PhD. Whether it will end up as a phononic fluidic cavity sensor, or whether we utilize the knowledge about optimization here at DTU and within CAM to change the boundary of the cavity in a different way, that's actually up for the future to decide and for Jaugen to decide. So I'm very much looking forward to seeing an improvement of these initial results. Before I talk about some of the other PhD projects that we have recently started, I would like to give a few minutes to introduce the Center for Acoustic Mechanical Microsystems for those not fully familiar with it. So CAM, as we are shortly called, is a joint center between the departments of mechanical engineering and electrical engineering. And it was founded on initiative of the Danish hearing aid industry, which is a big branch of industry in Denmark, and which fund and support us in multiple ways. We have staff and PhD students from both departments, and we also have multiple from highly trained personnel. So our mission is to advance the engineering expertise at the intersection of micromechanics and acoustics. And we do that by looking at from the three approaches that you've seen on the previous slide and that I mentioned in the very beginning. We're looking at the physical description, we're looking at modeling and optimization techniques, we're looking at from an application side, from a device and component perspective, and we are looking at it from a material and fabrication perspective. So what kind of materials do we need? What kind of process do we need to realize the structures that we have theoretically investigated, for example? And this comprehensive approach is really the idea behind CAM, that we look at it from multiple angles and try to find an optimal solution for a specific microacoustic problem, so a problem in a hearing aid or effects in a hearing aid that we want to get rid of. Other devices would be headphones, headsets, and other acoustic devices. We directly involve our industry partners. So they are involved in what we call expert groups. So they accompany all our projects along the way. They support them with their expertise. And of course, we also regularly interact with our partners to define mutual areas of interest where we want to focus our research on. In that aspect, or in that respect, I want to point out that we have a CAM day, a CAM presentation day in the end of November. So in, I think, 3 weeks from now, where we join forces with the Acoustic Technology Group to present the different research results of our students and also some concepts that we educate in our courses. So you're very much invited. It will also be a virtual presentation day because due to COVID, we are not allowed to gather so many people. So you're very much invited to join us. And if you need more information, just drop me a line and contact me. With this, I would like to take the remaining time to introduce the new project that we have recently started at CAM. I've already mentioned the phononic fluidic sensor system in detail that Jürgen has started in August. Then we have a joint project together with the Technical University of Munich, where Mikkel is investigating new methods, new tools, new code to achieve an efficient way to numerically model and optimize microacoustic devices with a special focus on the thermoviscous losses, which are very relevant at low frequencies. And here again, and when I talk about low frequencies in this regard, I'm talking about the audible range, so low frequencies around 100 Hertz or a few hundred Hertz. One other project that Jürgen has started also in September is dealing with MEMS microphones, which are more and more commonly used in hearing aids, but which bring about their own challenges and difficulties to integrate them properly. So he will explore them from those different angles that I mentioned before, to look at it, to create a physical description of the complete device, to look at both the MEMS part, which is basically a membrane, a capacitive membrane that reacts to an incoming sound pressure, but also the part around the MEMS device, so the packaging, the way it's placed in a hearing aid, and the way it's connected to the outside world. And find ways to get rid, for example, of its sensitivity to ultrasound. In the beginning of next year, Sujon will start a PhD working on new composite materials. So he will tackle the problem from the material and fabrication side to find new ways to build novel material properties for specific acoustical mechanical applications. And then we have two open positions, one on what are called balanced armature receivers. Those are the loudspeakers in a hearing aid. And we want to characterize them from a physical approach, from a physical understanding, model them, and then find optimal ways or maybe even new solutions to realize them in the aspect of hearing aids. The other new project is about mechanical contacts, modeling of with boundary layers. So we can actually assume hard walls and hard interfaces, for example, which makes things easier. On the other hand, we have also losses in the material itself, especially if we talk about 3D printed structures, which are polymers, plastic, and those are lossy materials. The numerical methods, or most of the numerical results that I've shown, actually include some kind of approximation of those material losses. And when you combine the whole thing with a fluid, with a liquid, then of course you have to consider the liquid losses, the viscous losses due to viscosity of the liquid as well, which has been done in those results. But you may have noticed, for example, for the phononic fluidic sensor, the concept, you got a very sharp resonance peak inside the phononic bandgap. This was a one-dimensional approximation, an analytical solution. It did include some approximation of the losses, but you still got a very sharp resonance peak, whereas in reality there was a wideband or more wideband, lower quality factor peak. So yeah, losses are an important aspect and a problem because you typically do not know them over a large frequency range, especially for things like polymers and especially for 3D printed polymers, which are layered structures. So it is difficult to estimate those losses, but yeah, you can approximate them.
Questions? Let me just check the chat. No. Then maybe I can ask a question. So I think you showed a very nice result for the metamaterial structure. You demonstrated that you had managed to increase the bandgap to unusually large range.
Yeah.
So what do you foresee in the future when we talk about audible acoustics? This is really a broadband area. Should we expect some years in the future that we can actually have structures that exhibit metamaterial behavior over a very wide frequency range? Or is it more that we can expect metamaterial components that address a more limited frequency range?
Yeah. So in literature these days you can already find vibration absorption materials that go down to 100 Hertz and below. Typically those results are based on numerical analysis, so you have to take them with a grain of salt. But some of the experimental demonstrations do show that it does work to a certain extent also at very low frequencies, especially if we talk about vibrations, so mechanical waves or elastic waves. If we talk about airborne sound, then as previously mentioned, the thermoviscous boundary layers, the thermoviscous losses at low frequencies would smear out the resonance effects, and therefore the loss mechanism that creates those broadband or creates the broadband response gets lowered and smeared out. On the other hand, this also benefits the broadband aspect of the whole thing because it's not a single resonance peak but a broad but lower resonance peak. You can affect a larger frequency range. And there are demonstrations of affecting audible sound, airborne sound, also down to a few hundred or even 100 Hertz, where the structural size of the element is basically centimeters. So there are demonstrations of metamaterials which do affect it down. But the practical implementation is always still the challenges, still the biggest challenge, because as far as I'm aware, the most successful samples are hand assembled, where you take, for example, metal spheres, so very heavy materials, coat them with a rubbery material and put them into an epoxy resin in a regular or semi-regular arrangement. This is hard to translate into into a reproducible fabrication technique. So whether we see them in practical applications and not just demonstrations from research, that is an open question indeed.
Okay. Yeah, thanks. There's a question from Carsten Bo Rasmussen. He says, would you like to tell us a bit about the experimental facilities that you're planning for the CAMP Center?
Yeah, I didn't include them in the slide because I was already at 45 minutes. So we are trying to expand the experimental capabilities by building a dedicated microacoustics lab. So the Microacoustics lab combines the aspects of the comprehensive approach that I've tried to illustrate with these three circles. And specifically it tries to combine the analysis with the fabrication. So we have fabrication capability on the micro scale, 3D printing, additive manufacturing, with the same machines and tools that the hearing aid industry and the hearing aid partners use, or at least similar tools. Then we have measurement stations, transmission measurement stations, where we can measure the acoustic and the elastic, so the mechanical transmission through the fabricated, through the 3D printed structure. When that whole lab will be up and running is an open question. Due to the COVID pandemic, we are a bit delayed from the side of preparing the lab, but the equipment, or some of the equipment, is ready to start already. And we actually begin first experiments probably next week, and at least still this year.
Yeah. Good. Thanks. Maybe I can ask another question. Oh, Rasmus, yes.
Thank you for your lecture. It was very interesting. Although I do know a little bit about the activity that goes on, it was very interesting for me to get this insight. And it's always wonderful to see when we have this convergence of the technical disciplines that allows us to do new things, in this case between mechanical and electrical engineering. You showed in the beginning some examples from microfluidics. Mm-hmm. Is this a research line that you are continuing, or has this been given up in light of your role as leading the CAM Center?
Which incorporate an acoustic component, where an acoustic wave is, for example, used to control the flow in a microchannel, to control the position of particles, mostly to collaborate. But I wouldn't put it away, especially